Okay, so welcome back to another video. So today we have a algebraic expression we would like to solve for. We have that we want to solve for any real number x such that the following equation satisfies. We have the floor of the log base 3 of x plus the floor of 1 over 3 plus the log base 3 of x is equal to 3. So this is actually not going to be as complicated as it is because of, we have two different types of functions. We have a floor and a log base, not natural log function, combined together into this algebraic expression. Not much needs to be done. So again, you have a floor function. You just utilize that definition of the floor function to get some idea on how that works. Then do a little bit of substitution. And then because if we're solving for that sort of, variable for x, and especially with the definition of the floor function, some inequalities are going to have to be involved / being utilized for, the workload entirely over here. Not much needs to be said. There's actually going to be a really short video since a lot of this stuff is the workload can be heavily simplified easily. If from first glance it looks complicated, but don't worry about that. You'll see where we're going with this. So why don't we actually just get started? So as by the definitions, let's actually suppose the following. We're going to let our variable, we'll let this be k. We're going to set that equal to the floor function of the floor of log base 3 of x, such that for k is an integer. So of course, that by the definition of the floor function, that's supposedly saying that, I shouldn't use the therefore symbol, this implies rather, so let me just put it this way. This implies that k is going to be less than or equal to the log base 3 of x, which is strictly less than k plus 1, of course, k being some integer. So now with that being the case, we can actually substitute the k back into here, so that means k and then plus the floor of 1 over 3 plus log base 3 of x is equal to 3. So therefore, let's subtract the k to both sides. So now we're just left with 1 over 3 and then add this. So, okay, I messed up again. So we have the floor of 1 over 3 plus log base of 3 of x is going to be equal to 3 subtract k. So with that being in mind, so now just to utilize that definition, essentially that's the same thing written as 3 subtract k, which of course is going to be less than or equal to 1 over 3 plus log base 3 of x, which is strictly less than 4 minus k. Okay, so with that being the case, now we can actually solve this compound inequality, meaning what we would do is that for first step, for 1, we're going to actually subtract the 1 over 3 to both the leftmost side and the rightmost side, leaving us with just the log base 3 of x just in the center of that compound inequality. So applying this, so subtract 1 over 3, so that means on the left-hand side, we're going to have that this is going to be 8 over 3, then subtract k, which is going to be less than or equal to just the log base 3 of x, strictly less than, so subtract the 1 over 3 to this side, so that means I have 11 over 3 subtract k. Okay, so now first thing is let me actually label these equations. This is going to come in handy to actually put everything together into one as the final step. So what I'm going to do is we're actually going to label, so of course this is going to be equation 1, that's going to come in handy, and then over here it's going to be equation number 2. And then the next step what I'm going to do is that we have our first equation over here, equation number 1, k is less than or equal to log base 3 of x, strictly less than k plus 1 with that definition. So if I utilize this, so plug this back into here, what I'm going to do is that I'm actually going to compare the leftmost side over here, k, with the rightmost side, and then do the same thing, but k plus 1 is going to be compared, the rightmost side with this is going to be compared with the leftmost side over here. So by applying this stuff, first thing is that we have the leftmost compared to the rightmost over here, so k is less than 11 over 3 minus k. So if I actually do some algebra, solve all that, so that means, so add k to both sides and then divide by 2, I have that k is going to be less than 11 over 6. Then we do the same thing, but we compare the rightmost side over here to the leftmost side over here. We're actually doing this to exclude the inclusion inequality and using the strictly in this case. So now an 8 over 3 minus k is going to be strictly less than k plus 1, implying that if you solve all this out, so subtract the 1 and then add the k to both sides and then divide it by 2, we're going to have that this is going to be 5 over 6 is going to be strictly less than k. Okay, so Now that we have these equations over here, well, the inequalities are what we're dealing with. So first thing I'm going to do is, well, not really first thing, but now the next step is rather, we're going to let k equals 1, which of course is an integer. We're going to plug this back into this equation and then plug it back into, this equation over here, equation number 1 and equation number 2. Now, really, k equals 1, I know that's, it's probably the obvious choice to use. So you might be thinking, can't you just use any sort of, integer for k? Well, 0 you can't, as it actually approaches negative infinity. The whole thing is going to be the log base of 3. Log base 3 of x is actually a positive function, so there are no negative integers allowed. And if you were to use 2 or higher, you can. The problem is that it's going to be a lot difficult to actually compare these inequalities together into 1. K equals 1 being the simplest choice, and actually if you plug that back in, it actually makes things a whole lot easier to, do the comparison behind all this. So now if we let k equals 1, and because I'll just say and because that it's an integer, we have that for equation 1 and 2 it yields. So I'm just going to do it like this. And equation number 2, we have that this is going to be 1 is less than or equal to log base 3 of x, which is strictly less than 2. And then for equation number 2 over here, we plug 1 to all this. We're going to have that this is going to be 5 over 3, which is less than or equal to log base 3 of x, which is strictly less than 8 over 3. Now, if you actually were to combine these compound inequalities together into 1, they're being compared for the log base x, log base 3 of x, we can actually come to the conclusion to say that we can say this is the inequality itself is going to be 5 over 3 is less than or equal to log base 3 of x, which is strictly just less than 2. So it actually makes things a whole lot easier. So now of course, the goal of the objective here is to find all real numbers x such that this satisfies the following. Well, we just need to get x by itself. And by doing so, we can actually just take the 3 base into all this. So that means 3 to the power 5 over 3 less than or equal to, so this is going to be 3 log base 3 of x. That's just going to get x by itself. And then I have 3 and then square. So now all this together is going to yield us the following. So of course, this is just going to be x on the middle. This is going to be just 9. And then over here, if you actually solve this out and get it to its reduced form, you can get that this is going to be 3 times the cube root of 9. So therefore, x actually falls between this interval. So I'll write it like this. X is therefore, for any real number x that's outside the following, it can be equal to 3 times the cube root of 9 inclusive, and then comma 9 non-inclusive. So therefore, that is our final answer to our algebraic expression over here. The solutions is following between this between these intervals here, inclusive, non-inclusive, and you can also just check these numbers out by yourself and plug them one by one if you feel like it, just to see that everything does satisfy the following like that. So yeah, that's pretty cool if you ask me.